For thousands of years, human beings have been looking up at the sky and making theories about the Earth, the planets, the stars, and the universe at large. At one time, the Magi and the sages of the world believed that the universe consisted of a flat Earth surrounded by the sun, the moon, and the stars. The visual observation at that time justified this belief. Aristotle, a Greek philosopher, advocated first that the earth was a sphere. In time, we also began to understand that the earth was indeed round and came up with rationalized explanations for the behavior of other celestial bodies. This gave rise to the geocentric model of the universe, where the Earth is at the center of the universe with the planets and the stars on the celestial sphere going around it. To ancient people, the geocentric model made sense as it seemed that the sun, the moon, and the stars rotated around the Earth once a day. The ground that they stood on seemed like a fixed point of reference, a flat plane from which to watch the circling cosmos. This theory survived all the way to the 16th and 17th centuries, by which time inconsistencies of this model began to surface, supported by observational evidence. The concept of geocentric universe was accepted as early as the 6th century BC. It was during this time that Pythagoreans proposed that Earth was circular based on observations of eclipse. Well, if you know, the shadow of the Earth on the moon during an eclipse is curved, suggesting that the Earth could be round. By the 4th century BC, this idea combined with the concept of a geocentric universe to create the cosmological system that most Greeks subscribed to. And it almost looked like this: the Earth at the center, the sun going around it, the moon going around it, well, all the stars around it, the moon and the sun. All right. According to Plato, the Earth was a sphere and the stationary center of the universe. The stars and planets were carried around the Earth on spheres or circles like this, arranged in order of their distance from the center. Thus, the moon, the sun, Venus, Mercury, Mars, Jupiter, Saturn, and the fixed stars went around the Earth in this order. Aristotle elaborated on this, placing a spherical Earth at the center and all other heavenly bodies arranged concentric, crystalline, or transparent spheres around it. That's Aristotle's contribution. Aristotle argued that the universe is spherical and finite. According to him, the Earth too is a sphere. It is relatively small compared to the stars, and unlike the celestial bodies, is always stayed at rest. These spheres moved at different uniform speeds to create the rotation of bodies around the Earth. So, all the rotation took place along these spheres. That's the Earth, that's the moon rotating, and that's the sun rotating, and so on. And all were immersed in an invisible and transparent substance called ether. He further described his system by explaining, earth, water, air, fire, and ether as terrestrial elements, and their natural tendencies gave rise to the positions of the earth at the center. So when you put these natural elements, which would sink to the bottom? Well, obviously, the heaviest element. Earth was the heaviest element, hence it moved towards the center. There you got. Whereas water, fire, air formed layers around it. That is referring to ocean, the sun. The sun is actually the fire. Beyond these layers, embedded in ether, lay all the celestial bodies. Some of the observational evidence contradicted this model eventually. For example, the luminosities of Mercury, Mars, and Jupiter were found to change over the course of time. Sometimes they look brighter, some other times they look a little dimmer. Also, it was observed that Mars and Jupiter sometimes seem to move backward in their orbits. Now, have you ever observed that? Sometimes they seem to sort of stop, then go back for a while, then go forward again. So they would appear to slow down, move backward for a time, then move forward again. This was referred to as the retrograde motion of these planets. The work of Ptolemy tried to resolve these issues by adding some modifications to the existing model. So we will see how these observational facts are actually explained in the later models. The Ptolemaic model tried to explain the change in luminosity of Mars and Jupiter and the retrograde motion of some planets in a very direct way, by assuming that each planet moved on a small sphere or circle like this. Each planet moved on a small sphere or circle called an epicycle that then moved on a larger cycle around the Earth. So that way he could explain that when the planets are farther away from the Earth, they are not very bright. When the planets are this part of their small epicircle, they are closer, they look brighter. Also, you can see the revolution of these planets along the epicircle. When they are going that way, they appear to be going backward. Is that right? They stop here, they go backward, and then they go forward again. So this way, Ptolemy tried to explain the retrograde motion of the planets, and also the fact that, the observed fact that some planets appear brighter sometimes and dimmer some other time. All right. During the Middle Ages, Christian theology supported the geocentric model to explain that God created the earth and placed it at the center of the universe and created the firmament with all the celestial objects on it to support life on earth. The Aristotelian Ptolemaic model was part of a marriage between faith and reason, championed by scholars like St. Thomas Aquinas. The separation of the universe into heavens and earth, with the earth at the center of creation and the heavens beyond, agreed with the Christian view of mankind being at the pinnacle of God's creation. This view of the universe was also accepted by the Islamic world at that time. But several Muslim astronomers challenged this view, prominent among them the Iranian scholar Abu Sa'id al-Zizi, who contradicted the Ptolemaic model by asserting that the Earth revolved about its axis, thus explaining the apparent diurnal cycle and the rotation of the stars relative to the Earth. Well, those were very bold steps those days. Another Iranian philosopher, Abu Rayhan Biruni, discussed the possibility of Earth rotating about its own axis. He's actually shown those in these pictures here. You can see these are the ancient writings of Abu Rayhan Biruni. Now, what did he say? He discussed the possibility of Earth rotating about its own axis and then around the sun. And you can see he also depicted the occurrence of night and day because of the rotation of the Earth. Now, this is a picture of his philosophy. In the 16th century, Nicholas Copernicus summarized his ideas in a treatise called Commentarilus, or Little Commentary. This described his ideas about the sun-centered model of the universe it is also called the heliocentric. Helio is helium, which is the abundant element in the sun. So heliocentric is sun-centered. So this is the first serious attempt for the heliocentric model, that is the Copernican model. Now, Copernicus's heliocentric model put forward several important principles. I have put them down here for you to read. And you see the stars are immovable. Their apparent daily motion is caused by the daily rotation of the Earth. And the Earth is moved in a sphere around the sun, causing the apparent annual migration of the sun. And he said the Earth has more than one motion. And we know that now. The Earth rotates as well as revolves around the sun. The Earth's orbital motion around the sun causes the seeming reverse in direction of motions of the planets. In other words, he also gave explanation of the retrograde motion of the planets. Now, how does that happen? Now, that's the sun, that's the Earth. What happens is when the Earth passes Mars, can you visualize that? As the Earth passes Mars, for a while we see the Mars going backward. So by placing orbits of Mercury and Venus between the Earth and the Sun, Copernicus was able to account for changes in their apparent luminosities. Now, when would these planets, some of these planets, appear to be brighter? You can see Mars is now closer to the Earth. It looks brighter. But there are times when Mars will be somewhere on this position, and then Mars will look less brighter. Same about Venus and Jupiter. When they are on the farther side of the Sun relative to the Earth, they appear smaller, less brighter. When they are on the same side of the Sun as that of the Earth, they appear larger but horned, well, just like the face of the Moon. It also explained the retrograde motion of the planets, as I just said. Like Mars and Jupiter, by showing that Earth astronomers do not have a fixed frame of reference, but a moving one. The Earth is actually moving, and we are standing on that moving Earth and observing these planets, and the retrograde motion is caused by that. Is that right? Now, retrograde motion is an illusion caused by the moving Earth passing the other planets in their orbit when they appear to go back, just like when a fast car passes a slow car on a highway. The passenger in the fast car sees the slow car moving backward. Haven't you observed that? This is the same phenomenon. As the fast car passes the slow car, the passenger, that is the observer on the Earth, sees the slow car moving backward, and this is the illusion, and that is the process of the retrograde motion of the planets. Now, another astronomer who made significant contribution in the 16th century is Tycho Brahe, who developed comprehensive methods for observing the skies. In addition to discovering the existence of supernovas, his parallax measurement showed that the comets are much farther away than the moon. His extensive measurements of the position of Mars in the skies led Kepler to discover the laws of planetary motion. We will discuss that later in this lesson. He also did detailed measurements on stellar parallax. Now, I talked about parallax a couple of times before, but what is parallax? We need to understand that because we will be using that as we move on. Parallax is the apparent shift of position of a nearby object against the background of distant objects. To understand this, I'm going to ask you to do a simple exercise. Hold your forefinger vertically in front of your eye, about arm's distance from your face, and align it with a distant object like the edge of a house or the edge of a window or a tree outside. Now close your left eye and observe the position of both your finger and the distant object. All right? Now close your right eye and observe the positions of both. Which has shifted position most? Is your finger or the distant object? Well, you can see what parallax means. This phenomenon is what we call parallax. Now, in the trial that you just did, the baseline of the two observations are the distance between your eyes. Now here, the diagram shows how astronomers actually measure parallax of stars. Now here, an astronomer is making an observation of a nearby star, and that star is about 1 parsec away. Well, 1 parsec is approximately 3.6 light years. Well, so that's the closest star we can find. Now, when the astronomer observes from here, he observed the stars to be in this position. Is that right? Now, after 6 months, the Earth moves to this position, and the astronomer again observes the near star, and he finds the near star to be in this position. And this angle is what we call the parallax angle. Now, if you are able to measure the parallax angle, we can measure the relative distances of these objects. And that is a very important study in astronomy. Although Copernicus' theory contradicted the theological position. It only attracted rather mild condemnation from religious authorities. So Copernicus really got away without much condemnation. Within a few generations' time, Copernicus' theory became more widespread and accepted and gained many influential defenders in the meantime. Galileo's discovery of the telescope, again in the 16th century, allowed him to resolve what was seen as flaws in the heliocentric model. Some of the important observations he made with his telescope are mountains and volcanoes on the moon, sunspots which moved on the sun, individual stars within the Milky Way, phases of Venus like those of the moon. All these are observations Galileo was able to do with his telescope, the newly discovered telescope. He also observed that Jupiter has moons of its own. In fact, 4 of the moons were observed by Galileo using his telescope. Well, it's interesting to note that Galileo's support of the Copernican theory landed him in jail. Copernicus was not punished, but in supporting Copernican theory, Galileo was punished. The German mathematician Johannes Kepler used the observations made by Galileo and Tycho Brahe to come up with his laws of planetary motion. Now, Kepler's laws of planetary motion are summarized in 3 statements. These are the 3 statements. They're important and you must be familiar with it. Now, what are those statements? It said the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. I'll explain that. The second statement says, an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time as the planet goes round the sun. And the third statement said, it's a little difficult to understand, but we will persevere. The ratio of the squares of the periods of any 2 planets is equal to the ratio of the cubes of their average distance from the sun. Now, what is the meaning of period of a planet? Period of the planet is the time taken for one complete revolution around the Earth. Tell me, what is the period of Earth? The Earth's period around the sun is 365 days, which we call 1 year. Now, what is the average distance of the Earth from the sun? We talked about it before. It is called 1 astronomical unit, and it is 150 million kilometers. So what does the third law says? It says the square of the period varies directly as the cube of the average distance of the planet from the sun. All right, we will write down that and learn and talk more about it. Now, this is an ellipse. Now, how is it different from a circle? Now, you can actually draw an ellipse like this. What I would want you to do is fix a piece of paper onto a table and fix 2 thumbtacks on it. All right? And then take a loop of string and let it go around the thumbtacks so that this loop of string can slide over the thumbtacks easily. All right? Then take a pencil, as it is shown here, stretch the loop of string and move the pencil around on the paper, making sure that the two segments of the string are always taut. Now, that means you are going to trace a path, and the path will be this. This is an ellipse. Now, one important property of ellipse, if you add this distance to this, at any position of the pencil, the sum of these two distances will remain a constant. That is, when the pencil is here, adding that distance to this will be the same as adding this distance to this. It is true for any position of the pencil. Now, the positions of the thumbtacks are called foci. Foci is the plural of focus. So, I said I will explain this. We said the sun is located at one focus. So, according to Kepler's law, a planet like Earth goes around the sun in an elliptical orbit, and the sun is at one focus. That's what the first law means. All right. Now, these illustrations actually explain the second law. What the second law says? The second law says the line joining the planet to the sun sweeps out equal areas in equal intervals of time. That means if the time taken for the planet to move from here to here is, say, 10 minutes, then from here to here is also 10 minutes, those two areas will be the same. And the time taken to move from here to here is 10 minutes. This area also should be equal to this. And if you watch this animation here, because the areas covered in equal interval of time have to be equal, the planet gets faster as it gets close to the sun, and speed reduces as it moves away. So the planet goes faster here and slower as it goes away from the sun. Actually, this observation was made by Tycho Brahe many years ago, and Kepler actually used that to arrive at his conclusion here. So that is the second law. What does the second law say? It says the line joining the planet to the sun sweeps out equal areas in equal intervals of time. What is the consequence? The consequence is the planet moves faster as it gets closer to the sun, and it slows down as it moves away. That's what it means. All right. Now let's talk about the third law. What does the third law say? It says the square of the period. Now we will denote the period by the letter T, and the average distance of the planet from the sun by the distance R. Now the law says T squared, the square of the period, varies directly as the cube of the average distance. Or if you divide T squared by R cube, it will remain a constant. Now, this constant has the value 1 provided we measure the period in Earth years and R the average distance in astronomical unit. Remember, this has a value 1 only when the period T is measured in Earth years and the average distance in astronomical unit. Now, here I have given the period in Earth years of all the planets. The period of Earth is 1 year. Its average distance from the sun is 1 astronomical unit. And you can see T squared divided by R cube is 1. All right. Now, Mercury, the period is 0.241 Earth year. its distance is 0.39 of an astronomical unit. Now, can you calculate the square of this divided by the square of this and see whether you get 0.98, which is close to 1? And you can try this for all the planets. I'll tell you what you can do. You can draw a graph with t squared on the vertical axis and r on the r cube, because you see t squared is directly proportional to r cube. That means if you draw a graph of t squared on the vertical axis, r cube on the horizontal axis, what kind of graph would you expect to get? Make a guess. If you remember in your elementary algebra, y equal to mx, it means y is directly proportional to x. If you draw a graph of y on the vertical axis, x on the horizontal axis, it will be a straight line through the origin, and y equal to mx tells you m is the slope of that graph. Now here, t squared over r cube equal to 1 means t squared equal to 1 times r cube. So if you draw a graph of t squared on the vertical axis and r cube on the horizontal axis, it will be a straight line and the slope will be 1. Well, this is where I have stated that again. So Kepler's third law states that the square of the period of revolution of a planet is directly proportional to the cube of its average radius. So if t is the period of a planet and r is its average distance from the sun, this means that the ratio t squared over r cube will remain a constant. And this constant will have a value 1 when t is in Earth years and r is in astronomical units. And here I have shown you the graph of how the graph will look like. Well, I've actually done a graph here. These are the values of t squared and these are the values of r cube. I've actually done the graph on Excel. Now look at this. T squared values I put on the y-axis and r cube values on the x-axis, and I measured the slope for you. Now, how do you measure the slope of a graph? Well, slope of a graph is delta y divided by delta x. In other words, change in the value of y divided by change in the value of x. Now here, I use change in the x value. Look at this. This is 50,000 and this is 10,000. So the change here is 50,000 minus 10,000 is 40,000, isn't it? I'm missing a 0 there. Similarly here, this is 50,000 and this value is 10,000. And so the change is 40,000 e squared, and the change in x is 40,000 astronomical unit cube. And if you take the slope, change in y divided by change in x, that is 1. All right. Okay, let's move on. Now, in the form of an equation, the third law can be written as t squared equal to r cube. Actually, in the strict sense, it should be t squared equal to k r cube, where k is a constant. And in our case, when t is measured in Earth years and r is measured in astronomical units, that constant has the value 1. So in this case, t squared equal to r cube. So this is possible only when t is measured in Earth years and r is measured in astronomical unit. All right, let's do a little calculation. Find the average distance of Mercury from the Sun if its orbital period is 88 Earth days. Well, we will say when t is measured in Earth years and a or r is measured in astronomical units, then t squared equal to r cube. I should correct that to r, the average distance of the planet from the Sun. Alright, so what are these values for Mercury? The period is 88 Earth days, but in order to use this equation, the period must be in Earth years. So we first convert 88 days to years by dividing by 365. So the period of Mercury is 0.24 year. In other words, in 0.24 year, Mercury will go around the Sun once. So we will put this t equal to 0.24 and calculate r. Look at that. So we got 0.24 squared equal to r cube. Can you use your mathematical skill to find r? It's a very simple thing. Look at the way I'm going to do that. So r equal to, because this is r cube, we take the cube root of the other side. R equal to cube root of 0.24 squared. And cube root of 0.24 squared is 0.24 to the power of 2/3. And can you put that in your calculator? Now remember, when you put this in the calculator, do like this. Type in 0.24 and then use the caret for power. Caret. Then use parenthesis. You put 2/3 in parenthesis. So once again, type in 0.24, caret for the power, parenthesis, 2 divided by 3, parenthesis closed, and you get 0.39 astronomical unit. So the distance of Mercury from the Sun is 0.39 of the distance of the Earth from the Sun. All right, let's do another one. The average distance of Uranus from the Sun is 2,887 million kilometers. What is its orbital period around the Sun? So here, the distance r is given. We need to find the period t. So where do we start? Again, we start with our equation, t squared equal to r cube, emphasizing that t is measured in Earth years and not r is measured in astronomical unit. All right, remember the r given here is in millions of kilometers. We need to convert this to astronomical unit. How do you do that? How many astronomical unit is 2,887 million kilometers? Can you do that? What is one astronomical unit? One astronomical unit is 150 million kilometers. So if you divide this distance by 150 million, you get the number of astronomical units in it. So here I have done it for you. R equal to 2,887 million kilometers. Converting that to astronomical unit, how? Divide that number by 150 million. Well, because both are in millions, you need only do 2887 divided by 150. And that gives you 19.2 astronomical unit. That is, well, that is the value of r. So we got t squared equal to r cube, where r is 19.2. Okay, just as we did in the previous case, can you solve for t? T squared equal to this right side. So how do you find t? You've got to take the square root of the right side. And That's the same as t equal to 19.2 raised to the power of 3 over 2. You see, if you know your algebra, when you have power with the denominator, that denominator tells you the type of root. So this denominator is 2 means you take the square root of 19.2 to the power of 3. That's what it means. All right, do it on your calculator again. Type in 19.2 caret parenthesis 3 divided by 2 and see if you get 84.1 years. Another one. All right. Galileo is often credited with the early discovery of 4 of Jupiter's many moons. The moons orbiting Jupiter follow the same laws of motion as the planets orbiting the Sun. But remember, you cannot use t squared equal to r cubed there. But the equation should be t squared equal to k r cubed. T squared is directly proportional to r cubed. So one of the moons is called Io. Its distance from Jupiter's center is 4.2 astronomical units. And it orbits Jupiter in 1.8 Earth days. So we got R and T for Jupiter's moon Io. What that helps you to do is use the values of this R and this period T to find that constant K, and then use it for the next moon. Another moon is called Ganymede. It is 10.7 astronomical units from Jupiter's center. Make a prediction of the period of Ganymede using Kepler's third law. Forget about that word. So t squared is proportional to r cubed means that the value of t squared over r cubed will be the same for both the moons. Now in this case it will not be 1. Why? Because 1 is applicable only for the Sun and its planets. This is Jupiter and its moons. But the law t squared over r cubed is a constant will apply there. So we will first find for Io the value of t squared over r cubed. T is 1.8 Earth days, so this t squared is 1.8 squared, divided by r is 4.2 astronomical units. So t squared over r cubed for Io is 0.0437. Now, this value of t squared over r cubed for Io should be the same for Ganymede also. So we will take this value and set it equal to t squared over r cubed for Ganymede, right? All right. So for Ganymede, the same value must be equal to t squared over r cubed, where r is 10.7 astronomical unit. And now, use this to solve t squared first, and then t. You notice that 10.73 is the denominator here. So t squared can be obtained by multiplying this to this. You see the denominator, cross multiply. So we get t squared equal to 0.0437 times 10.7 cubed. That is 53.5 days squared. This is squared. And therefore t is 7.3 days. Now, don't get disheartened with these mathematical problems. I'm not going to emphasize the mathematical problems too much, all right? But you must just know the basic concepts that we are discussing in here. All right, we shall stop in here and continue with another lesson sometime later.